Great pleasure to have you here, Kathryn, and we're all looking forward to your presentation. And I had the pleasure of listening to a plenary talk by yourself on Hawaii at a conference this summer, and I was blown away. So I'm looking for more of this now. So great honor to have you here. Thank you for making time for this. And if it's okay, I'll stop sharing and I'll give the word to you now.
Thanks very much, Val. I hate those sort of introductions because then you can only go downhill from there.
No, not in your case.
So I'll go ahead and I'll share my screen again. There we go. Can you see that okay? Good, yeah. Good, right, perfect. Okay, so Val and Fran asked me to come and talk about critical raw materials for the energy transition, which is the area that I do a lot of research in. As Val has said, I sort of started out with the rare earth elements, but I've moved into a wider kind of set of research on a whole range of critical raw materials. And I understand that some among you are geologists, but some of you aren't. So there's not going to be so much geology in this talk. It's going to be a kind of overview, introduction to some of the concepts. And the really important basis, if you like, for all of this is, of course, climate change. And this is a really nice representation, I think, that really visually illustrates climate change and, you know, why we should care. These are global temperatures from 1850 to 2021, showing through the medium of the coloured stripes. This was created by Ed Hawkins at the University of Reading. Basically, dark blue colours are years when the temperature globally was much cooler. The dark red colours are the temperatures when the years when temperatures were much hotter. And of course, you know, it really demonstrates how much change there has been over just the last 170 years or so. So of course, the point of all of that is that we have to develop new technologies that allow us to tackle climate change. And one of the latest component reports of the IPCC's assessment report was looking at those technologies that we're going to use to try and tackle climate change, and showing how for things like solar power, onshore and offshore wind power, and for electric vehicles, the cost has been going down enormously over the last couple of decades. And so the adoption is really going up rapidly. We're looking at much more electricity across Europe in particular, being produced by solar panels and by wind power. And we're looking at much more use of electric vehicles. In fact, if you look at this figure from the International Energy Agency, from their Global Electric Vehicle Outlook that they release every year, this is the change in the amount of electric vehicles worldwide since 2010. And you can see, basically, in 2010, there were no electric vehicles on the road to speak of. But now in last year, in fact, we're looking at over 16 million electric vehicles. Now, a lot of that is driven by China, and of course, they're not all electric cars. China has a lot of electric bikes as well, and electric scooters that people are using. But it's also increasing, as we know, in Europe, and even the USA is now starting to see an increase in the use of electric vehicles. So this is a really huge change, moving away from the internal combustion engine and towards electric vehicles. And that is certainly one of the ways we're going to reduce CO2 emissions. But the point, of course, and the reason that I'm talking about this is that that comes with another requirement, because this is a lovely quote from Sally Malley and others in 2017 in Nature. And they said, a transition to a low carbon society will require vast amounts of metals and minerals. The world cannot tackle climate change without an adequate supply of raw materials to manufacture clean technologies. And that was true in 2017, and it's even more widely recognized now. We need a huge range of different metals and minerals to build all of these technologies. And where will they come from? Well, there is an absolute truism that a lot of people say, that I've shown here at the bottom, and that is, if it can't be grown, it must be mined. All of these raw materials that we need, ultimately, they have to come out of the Earth's crust. There's no other way to access them for the first time, if you like. So when we're talking about critical raw materials, let's just jump right in and talk about some of the things that we mean here. And really, this is a question of pretty much half of the periodic table that we're going to be using in all of these technologies we need for the energy transition. So for example, in those electric vehicles, we need batteries. Now, batteries, of course, we've all heard of a lithium-ion battery. So of course, they need lithium, but a whole range of other raw materials like cobalt, graphite, which of course is a form of carbon, nickel, manganese, and vanadium are all potentially necessary for batteries. In our wind turbines, and indeed in the motors that drive our electric cars, we have high-strength magnets. And there's a whole range of different possible ways of making those magnets. But one of the most important is a rare earth element bearing magnet. And of course, Val just mentioned rare earth elements. I'm not actually going to talk about those too much today, but that's a whole group of elements in the periodic table. And among those, there are three, neodymium, dysprosium, and praseodymium, that are really essential for these high-strength magnets. Then the solar panels. Solar panels, of course, need a whole range of different elements as well, different raw materials, including things that most of us don't ever think about at all, like gallium, indium, tellurium, and selenium. But if you want to have photovoltaic panels, you need those elements. And hydrogen. We sometimes hear talk of the hydrogen economy and how this is going to be the answer to all our ills. But in fact, if you want to make hydrogen by electrolysis, so you want to make what we call green hydrogen, then you need an awful lot of platinum group metals, which of course, as I'm sure many of you know, that's the rarest among the metals really that we can access. But also, if you want to make your electric vehicles, they have to be strong yet light in terms of the bodywork. And for that, you need some really impressive modern alloys. So you need things like aluminium, niobium, magnesium, and titanium. And then, of course, we've got all this wiring and cabling to allow us to electrify our whole economies. And we need things like copper, zinc, and silver for that. So really, it's a whole range of different raw materials, a whole range of elements from the periodic table that we need. And this is from an International Energy Agency report about the role of critical minerals. And it just illustrates how much more we need in terms of minerals for clean energy technologies. Now, this diagram is slightly skewed because it doesn't show steel or aluminium, which are actually the biggest components of any of these technologies. And they, of course, are needed in both the conventional technologies and the new clean energy technologies. But that aside, you can see that for an electric vehicle, the amount of different minerals required is substantially more, probably about 5 times more than was needed in a conventional internal combustion engine car. And similarly for offshore and onshore wind and for solar, again, you need a whole range of different raw materials that you didn't need if you were burning coal or natural gas for much of your energy. So it just demonstrates how many more different raw materials we're going to need and how much more of those raw materials we will need. And if we just focus in a little bit on lithium-ion batteries, and this is from a report published by the UK Critical Minerals Intelligence Centre, which is part of the British Geological Survey. You can see the website address there. Just focusing in on a lithium-ion battery, and we all think, well, of course, it requires lithium. That seems obvious. But in fact, of course, each battery is made up of a whole series of connected lithium-ion cells. And those cells have, of course, an anode and a cathode. The cathode, that chemistry can be really varied, but most commonly it includes nickel, manganese, and cobalt. The anode is typically made up of graphite, so a form of carbon. And then you have an electrolyte through which the lithium ions can migrate during charge and discharge. Lithium, of course, is one of the most conductive elements and therefore really important for batteries. And there are all sorts of other battery chemistries being developed. There's huge amounts of research going on to try and find the most efficient batteries that use the least in terms of the different raw materials. Nearly all of them still use lithium. And one of the things that I find really interesting is that whenever people talk about, oh, but we'll use this new battery or that new battery, there's always still raw materials involved. You can't, at least not yet, you can't make batteries out of air. So whatever we do to store energy and to drive our electric vehicles, whatever kind of battery we use, it's going to need raw materials. So I'm talking here about critical raw materials, and that sort of terminology is very tightly defined, actually. Sometimes people think it just means critical to the energy transition, but there's more to it than that. So criticality is normally based on two axes. And one of those axes is how economically important is that particular raw material, and that can change between countries. You know, what's economically very important in Australia may not be terribly important at all in Finland, for example, depending on the manufacturing industries in that country. And then the other axis is risk to supply. How easy is it to get supply of that raw material? And if something is economically important, but has really significant risk to supply, then we refer to it as being critical. And the European Union's been making lists of critical raw materials for the EU since about 2012. And this is the latest one, published in 2020. This is rather small text, apologies, but you can see that they've plotted those two axes, and they've plotted a whole range of different raw materials on there. The ones in red are what they consider as critical. And I'm just going to highlight a few of the raw materials that we've already talked about a bit. So right up at the top there are the rare earth elements, and they are considered in just about any criticality assessment as having the highest risk to supply and therefore being very critical. If we look at sort of right-hand corner here, then we've got cobalt showing up as both economically important because of its use in batteries, but also having quite high risk to supply. And there's other things in that sort of area like niobium, magnesium, tungsten that are considered to have supply risks, which I'll talk about in a moment, but also to be very economically important. Interestingly, you can see that in this figure, and this is 2 years ago, remember, both graphite and lithium appear to be not that economically important and have relatively low risk to supply. This is because the change in the amount of material we've needed for batteries has been so rapid. If you remember the electric vehicle diagram, the uptake of electric vehicles is happening so quickly. I'm fully prepared to bet that in next year's reassessment of the EU criticality matrix, both graphite and lithium will have moved quite a long way to the right of the diagram. And then if we look lower down here, nickel, which is used in batteries, and also manganese is down there in that bottom quadrant as well. These raw materials are seen as having very low risk to supply, even though they're quite economically important. And that's because these are produced on such large scales that they're really produced all over the world. But when we talk about risk to supply, what we're really talking about is concentration of mining or production of those raw materials in a small number of countries. And perhaps those are countries that we don't entirely have faith in to always be able to supply or always want to supply the raw materials that are needed within the EU. And so, for example, this is just looking at the share of mine production back in 2020. And this is for the rare earth elements. And you can see that China produced something like 2/3 of all of the world's rare earth elements in 2020. And that Burma or Myanmar produced another significant segment. And in fact, all of that material from Myanmar goes straight to China and goes straight into the Chinese market. So in fact, China has control over probably about 80% of the entire rare earth element market. The only other significant production is from Australia and the USA. But in fact, even the USA's production goes into China pretty quickly for processing. So the rare earth elements are considered to have real supply risk just because China has such strong control over supplies of the rare earth elements. If we look at cobalt, it's a slightly different kind of story. Now, something like 3/4 of the world's cobalt comes from the Democratic Republic of Congo. And that's considered to be more of a concern, mostly really because people perceive all sorts of problems with the mining industry in the DRC. Rather than that being a true risk to supply, it's more about the nature of that mining industry. But what you can see with cobalt is that there are a lot of other countries producing it, just in much smaller amounts than the DRC. So it's still considered to have a supply risk, but not as significant as the rare earth elements. And then if we look at lithium, interestingly, this is a slightly misleading diagram because it's quite difficult to compare, as I'll show you later, the different types of lithium and the different amounts of production. But what you can see here is that Australia is a very dominant country in the production of lithium. Argentina and Chile are also very important. Now with lithium, that means that the EU really isn't concerned about risks as such to supply. There's no reason to think that Australia or indeed Chile or Argentina are going to stop supplying the EU anytime soon. The concerns about lithium are purely about that increase in demand that we're expecting to see because of the increase in electric vehicles and therefore batteries needed around the world. But one point to think about with all of this is that when we're talking about critical raw materials, we're really often talking about quite a small part of the world's mineral and metal raw material usage. And this diagram illustrates that. So if you look on the left-hand side, the left-hand bar illustrates all of the metal and ores mined worldwide every year. And what you can see is that iron ore, the base material for steel, of course, is mined at the rate of over 3,000 million tons every year. So that's huge. That's by far the biggest raw material, biggest mineral and metal raw material that we are mining. All other metal and ores form the blue bar in that left-hand side of the diagram, and that's 215 million tons in total. And you can see the middle bar here shows some of the other fairly significant raw materials that we're mining. Aluminium at around 60 odd million tons, manganese at about the same, chromium, copper, zinc. These are pretty significant still. There's a lot of mines to produce that amount of raw material, just not on the same scale as iron ore. But when we go into the critical raw materials, what we're actually looking at is still a tiny bar here, a tiny box even in that middle bar. And for what's called here technology and precious metals, we're only looking at 1.2 million tons being mined every year. So a tiny, tiny percentage of the amount of iron ore. And we can look at things like tin, molybdenum, but then here's lithium. This is from a couple of years ago now. So that 100,000 tons of lithium has certainly increased. The rare earths still at sort of 36,000 tons, and things like gold and the platinum group elements at really tiny amounts that we produce every year. So these are relatively small markets, all things considered, compared with certainly with iron ore. Having said that, of course, they are growing fast. And the growing demand for minerals, again, I'm going back to the International Energy Agency. I do recommend this report, it's well worth looking at. To look at the expected change in demand for clean energy technologies by 2050. And they used a couple of different scenarios for how the world might change by 2050, how we might have changed our technologies that we use, how much we might have adopted electric vehicles, all that kind of thing. But whichever scenario you look at, we're looking at 4 to 6 times the amount of minerals needed by 2050 as we needed in 2020. That's all minerals overall. That's a pretty significant change. And the ones that we're going to need particularly, I mean, in this analysis, they suggested that we would need 40 times as much lithium in 2040 as we did in 2020. I think most people would say that's a bit of an exaggeration. 5 to 10 times is the more kind of common assessment. But having said that, we are seeing this incredible demand for electric vehicles, which means that we are going to need a heck of a lot more lithium. And then the other battery raw materials like graphite, cobalt, and nickel, we're still seeing a lot more demand for those. Even the rare earths, we're seeing 7 times as much rare earths needed in 2040 as we did in 2020. So really, the kind of key point here is we're going to need an awful lot more mineral raw materials. And then some of you will be thinking, well, that's great. Of course, we should be able to get a lot of that by recycling. And of course, that is absolutely true. And recycling is something that is going to be so important in terms of research, development over the kind of coming decades. But this is an illustration from the EIT raw materials of what the circular economy is all about. And you can see that you need to start, obviously, with primary resources, which you have to mine, you process them, and then they get manufactured into something, and then they get reused or recycled eventually, and they go back into that circular economy again. But you can also see that there's a lot of points at which there is waste. And that means because we always lose something, we're always going to need inputs to maintain that circular economy. So we're always going to need mining, but hopefully recycling is going to become more and more important. Nonetheless, if we look at the evidence, we can see that recycling is still some way off. And in particular, think about electric vehicles and batteries. That figure that I showed right at the start showed that in 2010, there were virtually no electric vehicles on the road. Now, I don't know about you guys, but most people would probably say they keep their cars for, or cars are kept for about 10, maybe 15 years, they stay on the road. And that means that if we had no electric vehicles in 2010, we're only just starting to get maybe the very first electric vehicles and their batteries available for recycling. Even by 2030, the amount of electric vehicles that are going to be coming back into being recycled is pretty small. And in fact, again, the International Energy Agency has done this research, and these diagrams are not the clearest, but the point here is, if you look at the yellow dots, those are the share of recycled minerals in total demand across 2 different scenarios. And what you can see is that at absolute best, maybe by 2040, we might be recycling around we might be providing about 12% of the cobalt demand by recycling, rather less for lithium, for copper, and for nickel. So it just shows that we're going to have to take quite some time to get to the point where we have enough material in that circular economy going around being recycled again, that we can have recycling dominant over mining. So the really key point is that over the coming decades, mining is going to be absolutely essential to provide the minerals that we need for the energy transition. So we need more and more of these minerals, and we're going to have to mine them at least for the next 2, 3, 4 decades, after which recycling should become more and more important. So when I talk about mining, and you're all going down a mine tomorrow, so you'll have the chance to look at what a mine is like if you've not seen one before. But we're talking not just about the physical act of mining, but about the whole value chain. And that value chain starts with exploration, actually working out where the mineral deposit is, identifying it, seeing what's there, characterizing it, which is what most of us do as geologists. Then we move to extraction, actually doing the job of mining, and you mine the ore, and of course then that ore has to be processed. It's not a finished commodity. You're not mining, for example, a rare earth element. You're mining a mineral, an ore mineral, as part of a rock. And so you have to do several steps of processing before you get the raw material you really need, and only then can it go into manufacture. Then it will become, it will be used, and finally you'll get to the point where you may recycle. And one of the really important points, certainly that is really critical to our understanding of critical minerals today, is the amount of time it takes to get into that value chain. So this is a nice diagram from visualcapitalist.com showing the life cycle of a mineral discovery. So say you start out with exploration, And you find, for example, a geological survey geologist like me has said, oh, there's some really interesting geology here. There is potential for a mineral deposit. So then a junior exploration company will go out and try and do some work to prove that that mineral deposit exists. And this is the start of this life cycle of the mineral discovery here. And at this point, everything is very low value, if you like. And you'll have geologists on the ground doing things like digging trenches, for example, like this trench here in Sierra Leone, and going and collecting soil samples, measuring, doing often quite low cost types of work to try and get an idea that there is a mineral deposit there. And that could go in for 4 or 5 years, and then there will come a point where perhaps they will have got enough data to persuade somebody to invest some money. And when money is being put into that exploration project, then hopefully you'll be able to do some drilling and obtain some drill core. Now, at this point, you've got real hard data of what's actually under the ground. And at this point, you might actually discover, you might be able to see and hold in your hands a bit of core through the mineral deposit. And here's a picture of some geologists looking at drill core in a quite well set up site. This is one where there's some money's gone in. And it's at this point that you may really manage to characterize a mineral resource properly and say, yes, there is something here, it's worth mining. But at this point, you could easily be 10 years after the start of exploration, certainly 5 years after. Then you've got to the point where you know there's a deposit there, there's a mineral deposit, it's exciting, you've characterized it enough. Then the way that mining works, what you've got to do is go away and get in an awful lot more money in order to mine, because building a mine takes tens, hundreds of millions of euros. And that can be really difficult. And a huge number of critical mineral projects around the world are at this stage. There is a mineral deposit there, whether it be lithium, graphite, nickel, cobalt, whatever it may be. The deposit is known to exist, but the next problem is getting the money and also getting all the permits in place to be able to actually turn that into a mine. And that's shown on this diagram as the orphan period, the kind of trough in the middle there. And that, for many mineral deposits, is the stage at which they stop. A really good example is in Sweden, the Norra Kärr rare earth element deposit, which about 7 or 8 years ago, we were writing papers saying Norra Kärr is going to provide all of the rare earth elements that the European Union needs. But it has not ever made it to the point of being a mine because of problems with permitting, which led to problems with cash flow and so on, so that it became stalled. But finally, in many cases, you will eventually get to the point where investors say, yes, it is worth investing and will put in that large amount of money. And then you do get to an operating mine. And here's an example of a nice mine in Namibia. This is actually a gold mine with some big trucks in the bottom, all looking this is a very nicely built mine, very well designed, very well engineered. But to do that costs a vast amount of money. And for many critical mineral deposits, up until certainly recently, the economics just haven't really meant that's been possible. So there's a lot of pitfalls along the way to building a mine. And then, of course, the other thing, once you've got your mine, is that I talked about extraction and processing. You start by mining essentially a rock. You have to get the ore minerals out of that, which means crushing up the rock, grinding it into relatively small pieces, and then using maybe gravity or magnetic techniques to separate out the minerals. Then you've got the mineral concentrate. That picture at the top right there is a lithium mineral concentrate, all bagged up and ready to be sent off for further processing actually in China. So there's huge amounts of steps to do before you have a raw material that you can ever sell to a manufacturer so that they can go away and start thinking about making, for example, battery cathodes. So let's look at an example of a particular raw material and the kind of situation for that raw material. And I'm going to look at lithium, partly because this is something that I'm doing a lot of research on at the moment, and partly because it is absolutely the hot topic because of its use in batteries. So again, this is from a report from the UK Critical Minerals Intelligence Centre. And this just shows you the change in global lithium production and prices over the last decade or so. And the coloured bars show you the amount of production up to 2020. We don't have figures for last year yet. And you can see that after about 2016, there was quite a significant increase in lithium production worldwide, mostly driven by Australia. So as we needed more lithium for batteries, Australian mines really started to ramp up and produce more lithium. But the challenge for them was that although they produced more supply, demand up until 2020 hadn't really changed that significantly. And as a result, prices, indicated by the black line, stayed fairly low. That was up until last year. And then suddenly everything has started to change, because that rise in electric vehicles has suddenly led to enormous requirements for lithium. And suddenly there's not enough supply to meet demand. And so we can see the prices spiraling up. And in fact, today I just saw on Twitter that lithium mineral concentrate has hit an all-time high price. So this diagram is probably a few months out of date, and since then it's only gone up further. So right now, interest in lithium is being driven by these high prices. So where do we get lithium from? Well, this is a map from the BGS website that you can easily download. And this shows you where lithium mineral deposits are known across the world. Where there's a large spot, that's an operating mine. Where it's a smaller spot, it's a known mineral deposit. And there's different colours here, which I'll talk about in a moment. The pale blue and yellow are brine and clay deposits, and the reds are pegmatites and granites, so solid rock deposits. I'll talk more about that in a moment. But here's the really interesting point, I think. You can see that all across Europe, there's plenty of known lithium deposits, and indeed we are missing several from this map. I can see, in fact, that there's very little shown in Scandinavia, but there are certainly lithium deposits in Scandinavia. There's very little shown here in Russia and Central Asia, not because they don't exist, just because we find it quite hard to get the details of where they are so we can put the spot on the map. But you can see across North America, across Europe, across Africa, plenty of known deposits, but very few actual mines. And indeed, even the ones that are shown as larger spots, for example, in Portugal, have only ever produced very small amounts of lithium. You can see that the mines of those bigger spots are really dominated by China, Australia, Chile, and Argentina. That's going to have to change. You know, worldwide, we're going to be mining lithium across the world. And actually, when people say, you know, is there a possibility of such and such a country having a lithium deposit? What I actually say is pretty much every country in the world, excepting most likely the Netherlands, will have a lithium deposit, because it's actually really not an uncommon mineral in the Earth's crust, and it's just not that difficult to concentrate. So here's a little bit of geology for you, just to talk about the different types of deposit that we have for lithium. And this is actually really important because there's a bit of a perception that lithium only comes from one type of deposit. So in fact, our number one main source of lithium is in solid rock deposits, so hard rocks that are mined in a conventional mine, usually an open pit mine that looks like a quarry. And that's lithium-rich pegmatites and granites that are mined particularly in Australia. And the top right picture there is an example of a pegmatite in Zimbabwe that is rich in lithium but hasn't been mined, in fact, in the past for tin. So you can see that's a classic hard rock mine. And when people say to me sometimes, well, you know, what's it like? What does the rock look like that you're mining lithium from? I say, well, it's a kitchen worktop. Because many of you will be aware of maybe kitchens with beautiful worktop surfaces that are made out of rock with great big crystals, or maybe you've seen, you know, some kind of posh building that is clad with rock with, again, great big crystals. Well, that's a pegmatite. And that's what we mine for lithium. So it's not something weird or unusual. It's a rock type that we see regularly, kind of in day-to-day life. And the other type of deposit that is actually a rock deposit is clays and associated kind of sediments that formed in the bottom of ancient lakes. So for example, in Serbia, the Adar deposit is like that. Sometimes in ancient volcanic calderas where there's been volcanic activity. But the other type of lithium deposit, and the one that most people have heard of, is lithium brines. And principally, we have a lot of the world's lithium coming from the salars or salt flats high in the Andes, where the brines are lithium rich, and they can, as they evaporate, so as those lakes dry out by evaporation, you concentrate the lithium in salts that are deposited within the salt flat. There's also potential to get lithium out of similar brines that just circulate actually in fractures in the rock. For example, in the UK, we have exploration for these kind of lithium brines in Cornwall. But for many people, the perception is that all of the world's lithium comes from the lithium triangle in South America, from the salars, the salt flats. And that definitely isn't the case. And mining these different deposits is done in quite different ways. So let's look at those salars first. And essentially those salt flats are enclosed basins. They're in the Andes, you've got big mountains all around, you've got volcanic activity going on, you've got very little in the way of rainfall. But what you do have is gradually over many years, over geological time, leaching lithium out of the surrounding rocks. And those surface waters are running into this closed basin, into these shallow lakes that have no real outflow. And then because there is so much sunshine, so little rainfall, you have evaporation within those lakes to give you salt flats. And those salt flats are very rich in lithium salts. So that's just a little diagram illustrating that. And then if you want to get the lithium out of those, well, what tends to happen, because of that climatic regime in those areas, it's just a question of pumping the brines out of the salars and putting them into artificial evaporation ponds, which means that you can then evaporate off the water and you're left with the lithium salts, which you can then easily process to create lithium chemicals that you can sell. And so that's a relatively simple, albeit still a large-scale industrial way of producing lithium carbonate. If you want to get the lithium out of geothermal brines in an area where you don't have the option to use solar evaporation, then you can use a technique called direct lithium extraction, which is a very clever process that the companies never want to give you the details of, by which things like selective membranes allow you to remove lithium from those circulating brines. But this is a developing technology. It's not used commercially in very many places. It sounds lovely. And once it's sort of working at full scale, it'll be fantastic. But at the moment, it's not used that widely commercially. So in fact, solar evaporation is still our main way of getting lithium out of brines. In contrast, solid rock deposits of lithium, like I say, these are pegmatites that are the sorts of things you see as kitchen worktops. These are pretty complicated rocks. But there's a whole range of them worldwide. There's lots and lots of solid rock lithium deposits all over the place, like I say, in a whole range of different countries. Now, interestingly, when you're at a lithium deposit, that area will contain a whole range of different rock types. So for example, the top image here is a cross-section through the Arcadia lithium deposit in Zimbabwe. And what you can see is that you've got, in yellows and blues and reds, you've got these sort of flat, almost tabletop-like bodies that are rich in lithium. And that's interspersed with rocks that are not rich in lithium at all. So if you're going to mine it, you're going to be taking out some lithium-rich rock, and you're going to be taking out some rock that's of no real interest to you. And that's going to be usually the case. That is often the case with many mineral deposits. And then that lithium-rich rock is made up of a whole range of different minerals. For example, if we're talking about a lithium pegmatite or granite, it probably contains quartz and feldspar, which we call gangue minerals because they have no real commercial value. It will contain lithium ore minerals, spodumene, which is a lovely word, is one of the main lithium ore minerals currently being extracted in Australia. And then it will contain ore minerals for other elements such as tantalum, for example, or tin. And these minerals are all integrating together. So that bottom right figure there, that's a map made with a scanning electron microscope. The little scale bar at the bottom is 500 microns, so about 0.5 millimeter. So this whole view is just a few millimeters across. And there's a whole range of different minerals in there. There's purple is muscovite, yellow is quartz, blue is albite, so feldspar. The red there is the spodumene, that's your lithium ore mineral. The point is, it just shows you how many different minerals there are. Even the lithium ore mineral is not easy to get out on its own. So you always have to have processing at site just to separate out those minerals. And at any mine, what they'll be doing is selling a spodumene concentrate. So they've done enough processing to separate the spodumene from the muscovite, quartz, etc. That spodumene concentrate normally has about 6% lithium oxide in it. So then it has to be sent off for processing. And that processing is a very involved job, usually using high temperatures, quite aggressive acids. It's a really serious industrial process. We don't know a lot about that processing, often because so much mineral processing for the whole world is done in China. And certainly pretty much at the minute, all of the world's spodumene that is mined is sent to China for processing. It's really important how much control China has over the value chains of all these critical minerals. And this diagram just illustrates that. So this is, again, a diagram from the UK Critical Minerals Intelligence Centre. And it shows at the top of that figure, you can see highlighted brine and spodumene or hard rock ore. Now, brine is relatively easy to process because, as we just discussed, you can do it by solar evaporation to produce lithium chemicals. And that all happens in South America, in Argentina and Chile. Whereas when we're talking about spodumene or any other lithium ore mineral, first of all, the beneficiation is done. That's the creation of the mineral concentrate. And that can be done in Australia or wherever the mine is. But then it gets sent off for the chemical processing to produce lithium carbonate or hydroxide, which is what you will sell to the battery manufacturer. And those chemical processing steps always happen in China at the moment. And then, of course, once that step has been done in China, it's pretty easy for China to say, well, now we'll sell this to the battery producers in China, giving China so much control over the whole value chains. I mean, the planning and preparation for this in China has been astonishing compared to everywhere else in the world. And this is just another way of showing that you start out by extracting substantial amounts of brine or hard rock, but you have a lot lost to mine tailings, so to waste in the mine. That's your gangue minerals that you can't use. That all goes for processing. Again, you have some loss to processing waste, and then that material goes off into batteries or perhaps into manufacture of other things that need lithium. So you have to mine an awful lot of material in order to eventually produce your batteries that you need at the end. And I've just been talking about, well, we know about lithium resources all over the world, and this is a pretty conventional plot for geologists, just showing grade, as in the amount of lithium in a deposit, against tonnage. That's the size of the deposit. Now on this figure, it's very hard to show brine resources because there is a problem with brine. It's salty water, it moves. That makes it very difficult to say exactly how much material is there. It's much easier to quantify. The orange is the pegmatite and granite deposits, the blue is the clay deposits. And you can see that the clay deposits are usually slightly lower grade, but they can be very large tonnage. Whereas the orange granites and pegmatites are often pretty high grade and variable tonnage. We know about all of these, we know they're there. And although the processing might mostly be done in China, it is possible to do it, it's all feasible. And yet there are so many challenges with opening new mines, especially in Europe. And this is really the problem. And this is the kind of final bit of this talk, is about the fact that even though we may, as geologists, we may know where to mine, or the exploration may have been done, the investment may be there, the idea of where it will all be processed, even if that is in China, may be known. Ultimately, so many lithium mines just never get, so many critical mineral mines never get to the point of being mines because of public protest, because of concerns around environmental and social impacts. And these are just great examples for lithium. The Jadar project in Serbia, which was to be mined by Rio Tinto, their mining license was scrapped after significant public protests. And in Nevada, again, the potential lithium mine at Thacker Pass is being blocked by a coalition of protesters. Now, of course, clearly, there's a need to protest if there is potentially going to be significant issues, environmental or affecting communities. But in many cases, particularly in Serbia, it's not quite clear what the basis for those protests was, you know, what the concerns were. But this is the absolute major challenge when it comes to our supplies of critical raw materials for the energy transition. We have to have these critical raw materials. We're not going to tackle climate change without them, because we are going to have to continue with internal combustion engines and burning fossil fuels for energy, unless we can persuade people worldwide to reduce the amount of energy they use significantly and to change their lifestyles significantly. And I think we all know that's going to be difficult, although it has to be part of the package. So we have to mine, and we have to fit that mining into the context of the Sustainable Development Goals and try and do it as well as possible. But although I think that's pretty well known among people who are involved in mining, public perception is simply that mining is bad and it's dirty. And the media don't help, because often they will cite the worst examples of mining, rather than perhaps talking about good practice. So for example, reports like this, how the electric vehicle boom is draining communities and the planet. What you often notice in these, for example, anything in the media about lithium tends to talk about concerns around the lithium triangle and around the mining in the salars in South America. You very rarely, if ever, see any reports about Australian mines, Australian lithium mines and problems there. And that's mostly because Australian mining, with some well-known exceptions, tends to be very well regulated, very carefully managed in terms of the environment, in terms of people living in the area, in terms of wider impacts on communities, in terms of governance, who is profiting, all that kind of thing. And that sort of thing doesn't tend to get talked about in the media, but that's what we need. We really need people to understand we have to mine, but we have to do it as well as possible and ensure that the governance and the environmental concerns and the social concerns are all as good as managed as well as possible. And that means we need to talk more about good practice, and just a couple of examples here. The first one is a PhD student that I've been collaborating with recently, who has been working on the big Ambatavi nickel mine in Madagascar, shown there on the left. And you can look up her paper in Nature Sustainability. This mine, when it opened, committed to protecting the forest. Now, Madagascar only has about 10% of its original primary rainforest left. And the biggest destroyer of Madagascar's rainforest is poverty. You know, local people need to use the forest as a resource because they simply don't have the money to buy energy from any other source, to build homes from any other source other than wood. They need to have subsistence agriculture, and for that they need to cut down the forest. So the mine committed to offering good jobs, funding to communities, and also to protecting the forests. And Katie's done some very careful analysis using mostly remote sensing to assess the local environmental impacts, and indeed has shown that the mine is on track to achieve no net loss of forest only a couple of decades after it opened. So in other words, as much forest would have been lost without the mine as was lost with the mine. That's pretty impressive, and shows that our assumptions that mines cause deforestation aren't always right. And similarly, if you look on the right, this is an example from a company called Minviro that we collaborate with quite closely. They've done life cycle assessment of the environmental impacts, and these are global environmental impacts, the amount of CO2 emissions of different types of lithium mining. And it illustrated, for example, that brine mining may cause concerns to people around the sort of local impacts, but on a global basis, it's much better than actually mining hard rocks and going through all of the processing you have to do with hard rocks. So the thing about this is it really gives the evidence upon which to have conversations. And for me, that is the critical thing. So just to kind of wrap up now and conclude, we really do need to mine critical raw materials in order to tackle climate change. Without critical raw materials, we're not going to be able to do anything. We're going to find it very difficult to reduce the rate of change in global temperatures if we don't use these critical raw materials. And we are not going to run out of them. There's plenty of these raw materials available to us in the Earth's crust. Recycling is going to be absolutely crucial, but it's just not the immediate solution, because right now the material's just not there to recycle. So we are going to have to mine, and we need to think about that as part of a whole supply chain, from exploration to mining to processing to manufacture. And all along that supply chain, we need good evidence-based assessment of social and environmental impacts on both local and global scales. And all mining companies need to work with communities, etc., to try and make sure that those impacts are minimized as much as possible. And that can be done. Mining can be done well. And if it is well governed at all stages of the supply chain, then that's the really crucial thing. And the final thing that I will say, and my final conclusion, is that we have very little critical raw material mining in Europe. And yet we know that the best governed, the best sort of rooted in evidence and rooted in modern technology, the best opportunities for that sort of mining are right here in Europe, and yet we're not doing it. And there's a question for you. Why is that? Thank you very much.